This robotic arm can feel. And through these haptic gloves, so can I. Welcome back to this newest video in the laser-induced graphene surgical robotics series. I'm Ian, and if you have been following along, aka by watching the previous two videos, and if you haven't, I encourage you to watch them, link in the description. You have seen me building these amazing sensors and trying to apply them onto robotic arms. And here we have done it. Today, we are combining all sorts of mechanisms together to form this grand prototype. So everything starts right here with this tiny little piece of laser-induced graphene in this particular pattern. So we take ordinary films called polyimide films, which is a slightly different, unique form of plastic as compared to, for example, what we use with tires. This plastic burns as opposed to how plastic normally just melts after you put a lot of temperature onto it. If we burn it with a CO2 laser, it will leave a trail of carbon behind. And if we do that, it will create this very nice porous conductive graphene structure. And under pressure, these porous layers compress and create more conductive pathways. And essentially this would change how electricity flows in it and therefore changes the electrical properties. It is simple physics in some sense, but then its application potential is amazing. Now, if you watched my last video, you know that I've been previewing about this idea of reactance measurement. However, what I found out is that after I built that little prototype of the reactance measure, what happens is that the signal frequency just could not reach my desired value. But here's the thing, resistance measurements are still pretty reliable and very nice to use. And sometimes the simplest solution might just be the better one. The reactance might be a little bit too bulky for our application in the first place. There's essentially just 24 hours from design to deployment, and it is less than $10 in making these materials. Everything is also biocompatible. The protective layer, which is called SEBS, is an elastomer, which also passed the USP Class 6 test for direct patient contact. And compare that to commercial sensors and custom solutions that cost hundreds or thousands of dollars, and full system costing millions, and takes weeks and years to produce. We can iterate designs incredibly quickly, and we can customize sensors for any needs that you want. And now let's get to the brain of the system, the Arduino. I have made some 5 or 6 Arduino boards on the bare minimum over the past month working on this prototype, and it serves as the central nervous system, and it reads analog values from the sensor about 60 Hz, which is 60 times per second. 4 servo motors gave us the precise control that we need on these surgical robots, and these 4 servo rotors control these discs under the robotic arm to give us all of the freedom that we need, just like the original system where they also need to control these 4 discs. And here is the frame that I've built to house the whole system. I have made some changes to this project called Project Salai, and I'll link his video as well down in the description. It is a beautiful design and it perfectly fits most of the things, but then I've made some changes to it to just help for my application instead. And now here is the Z stage, and it is just an Amazon product that you can buy online, in which it was controlled by a stepper motor and a 24-volt power supply. And it gives millimeter precision vertical movement. I connect onto my Arduino for precise control. And now here is the feedback system. As I've mentioned before, all of these mapping data is going to be thrown into the tactile feedback system. In order to achieve tactile feedback, what I've got is these convertible VR gloves that you can get online. They're not that expensive, and they're very nice because they have vibration motors on every single fingertip and on your wrist, and you can customize the intensity of vibration as well. So this allows me to just virtually just connect them up to a computer via Bluetooth and just upload intensity values whenever I want to. And at the final stage, this is the visual part of the whole system, this hand tracking ultra-red camera. So this camera, which comes from Ultraleap, checks out all of the joints at your hands and also detects if they're pinching or how far you could get from the camera itself. So combined with all of these systems, you don't actually have to have any training to use this robot. You just stick your hand into the glove, put it on top of the camera, and just control away. Just like how it is in the video. And so, what I've realized is that this technology does change sort of everything, and it's not just for surgery itself. During the process of this innovation, I've realized that regardless of latency and things like that, and optimization, this technology could be used for virtually anything that needs robot interaction. Actually, this technology could actually revolutionize everything and give a sense of touch to every robot that could exist. And this can not only promote security, this could also promote how us as humans interact with them. This entire thing is open source. Every component here is commercially available, and SCBS and Tollerene that are used in this process, you could just get them if you have institutional approval. The graphene fabrication process that we've documented as well also demonstrates that these things are not too difficult to fabricate as well. Check out episodes 1 and 2 in the end for detailed fabrication and programming tutorials, and also other insights that I have gathered during this time. And if you want to look into reactance measuring, you can look into that too. In the future, I'll be continuing to work on these things and improve my system along the way. Currently, I'm trying to contact various hospitals and companies to see if I could experiment this on an actual Da Vinci robot so that I don't have to work with my current control system. Although it's open source, it's not as good as the original. I'll see you all next time.